Welcome everybody at my presentation about implicits. So the reason for this talk is actually that I know lots of people who start doing Scala, get some of the basics, maybe touch a bit on implicits, but they are still a bit magical for everyone. And this presentation, I'm trying to explain this a bit more, see how the resolving works, and look into all those kinds of things. So we'll do a bit of an introduction of myself, then we'll take a look at implicits, see how the compiler actually resolves them, and if time allows, we'll look a bit into type classes as well. Okay, so let's get going. So a bit about myself. I'm a functional programmer. I did lots of Haskell at the university. Then I joined ING Bank, my current employer, where I teach and train people in Scala and more general in functional programming. They also more recently gave me the opportunity to pursue a PhD as well. So I'm looking into creating executable programs from from specifications about bank accounts and those kind of things. Well, if you want to know more about what we're doing with Scala at ING Bank, then please talk to me or send me an email. Okay, well, let's delve into the subject. So implicits. What are they and how can we use them? Well, let's start with the what. They're basically a way to get a value without explicitly referencing it. This sounds a bit fake, and it will become more clear when we look into some of the examples later. So in standard object orientation, we have is a relation and has a relation. So for example, a cow is an animal has a name, which can be a field of the animal in this case. Implicit adds something extra on top of this, namely is viewable as a. And you can, for example, say that a cow is viewable as a mammal. And this allows us to have small core interfaces and add rich views on top of them. And in the end, it gives us loose coupling because you have the small interfaces which are tightly have tight cohesion with views defined on them. So let's first look at some examples. I hope this is a bit readable in the back. So what you see on top is an example in akka. We have the actor ref, and on the actor ref this bang operator is defined. This is a tell. It's used to send a message to an actor. And we have one implicit parameter in the second parameter list, if that's visible there, which allows us to specify a sender. And from a user perspective, when you use it, you can, given an actor ref, use the bang method to send a message there, and the sender is implicitly put in there for you. Another example here is futures that we all know from the standard library. The second parameter is an implicit parameter of type execution context, which will take care of all the scheduling of threads. And it will handle all the asynchronicity. Well, when you normally use it, you don't have to really care about this, but you can, if you want, put in a different way that the thread management should be done. It's also used in the standard library of Scala. Here we see an example, traversable ones, with a method defined on its sum, and there's an implicit parameter of type numeric b. So this means that sum is only allowed to be called if this b, if there is a numeric b available for the element type b in this case. And in the end, we can use it like this. We can define a list, and then we can call sum on it, and it will just work. Maybe a more involved example is this. Who of you know Finagle? It's a RPC framework. And they provide this nice builder to build your client. So let's first look at the client builder here. So we have some type parameters, also has cluster, has codec, has host connection limit, and it contains some methods, and also the build method, which actually takes this implicit with this very long, weird name. But more important than the name is the type here. So this is called client config evidence. So only if there's an implicit available with these three values specified, then it will allow you to build the builder in this case. So here we see an example. If we make a builder and we only configure part of it, then we will see that for the first two ones you have a yes, and for the third one you have a nothing. And now, if you try to do the build, it will say the builder is not fully configured. And this is all powered by implicits. You don't need to grasp what is happening all here, but I just want to show a bit about what you can achieve by using implicits here. A nice thing to mention as well is the annotation on top. So the implicit not found here. And the compiler will actually use this message if it cannot resolve the implicit for you. And that's why we get this nice error message here. Builder is not fully configured. Also good to know is that this is actually a compiler error message. So this is all checked at compile time. If the implicits cannot be resolved, it will not compile. So given these examples, well, we see that implicits are quite powerful and enable lots of things. So for example, you can create DSLs with them. You can extend existing Scala values and collections and those kind of things to create very rich DSLs. You can use them for type evidence. We saw that in the finagle example and also a bit in the numeric B example on the Scala collections. Of course, well, if you can leave things implicit, you can leave code out, so it will reduce verbosity of your code. And they can be used in type classes, which we'll get back to in a bit. Another cool thing is that you can do something like dependency injection, where depending on which implicit is in scope, you actually use another dependency. And this is all resolved at compile time. And in the end, I think the most important feature is that you can extend libraries with it, for example, by using the type class pattern, which makes it really powerful. Of course, they can be a bit magical as well, and that has to do with the resolution rules. So which implicit is used when, and how can you find out what is actually going on here. If you look at just at code, you do the lexical examination of it, it might not be clear what is actually being called because things are left implicit. One thing to overcome this is to make use of your IDE. For example, IntelliJ really shows when implicits are being used and when implicit conversions are being used with the underscore, for example. And also you can use your IDE to see what implicit conversion is actually being used here. And of course, as Martin already mentioned in his keynote, he mentioned the blog post of Li Hao about the principle of the least power. Do not use implicits if you can achieve the same thing with something simpler in the language. But yeah. So, well, lots of theory and examples about implicits. So let's take a look at how they are actually used with some examples. So I made a distinction between these four types of implicits, and we'll take a look in the REPL on how we can use them. So you might notice this is a tool called represent, which you can make slides in the REPL, and it allows you to actually execute code that appear on the slide. So I will use this quite a lot. So, for example, here we have a simple method, give me an int, which takes one implicit parameter here, and will just return the implicit that it got. And we can call it like a normal method. Now, if I press R on the REPL, it will execute the code on the slide, and we can see the results here. So we define this method here, and we will get the result. So even though I added this implicit parameter here, keyword here, it doesn't do anything. You can also use it like a normal function. It becomes interesting if you actually have something in your implicit scope. So what we define here, implicit val, some int of type int with some value. now this sum int is available on the implicit scope, and if we now call this method without a parameter, it will try to make it work, and we'll look in the implicit scope, is there something for which I can make this work? We know that we defined it here with type int, so it will actually look inside the implicit scope, is there something of type int that I can use to make this compile? And if we run this, it actually works. So the result is 42 because it finds some int here. Another way that to get your implicits out of your scope is by using this implicitly. You might see it somewhere. This is nothing else than a simple method implicitly of some type t with some type parameter of what's it called, parameter for the method implicit something of type t, which it will return. So if we define something like this, it's also defined in the standard library. We can actually run it, and it will find something in the implicit scope for us. So this is just a helper method implicitly to summon the implicit value from your implicit scope, basically. So let's look at what is actually happening here. So I define this extra method SumCall, which will just wrap this give me an int, and then I can inspect it with Java P. So let's first run the code on the slide. Let's call Java P. So what we see now is the bytecode that is being actually generated under the hood. So for our method SumCall here, which is wrapping the give me an int, we can look inside and we see an invoke virtual here, sum method. So it will actually get the sum int, it calls the getter of the sum int, we'll put it on the stack, then we'll call the give me an int, which takes one parameter of type int, which will use the first value on the stack. So what we can see here is that in the compiled code there are no implicits anymore. The value is actually already filled in here. And this is a very nice feature. So what if we define another implicit int? So we already had the sum int defined on our implicit scope, and now we define another one, another int, and we try to run this. Whom of you thinks this will compile? Well, nobody, so you're all correct. The Scala compiler sees that there are two implicit ints in scope, and it cannot decide for you, so it will throw this error for you. So this is also a compile time error, I should say. So it can now find some int and another int, and it doesn't know which one to use. Okay, so let's take a look at implicit conversions. So first we define this normal method, which takes an int, converts it to a string, and adds some stuff in front of it. We can just call it as we would expect. And now we create a case class, in this case balance, which has a single field amount of type integer. We can create an instance of this. But what we want to do, for example, is call makeString on this balance. This will not work because the makeString method expects an integer and you pass it a balance, so well, this doesn't work. But we can make it work with implicit conversions. So what we do here is we bring an implicit def in the implicit scope here by defining it like this. So we have a method named balance_int, which will take one parameter of type balance, will output an int, and we'll just use the amount inside the case class for now. So now that this is in scope, it will actually work. Oh, it should work. I maybe should run this first to make it available. Yes. Okay, so now it will work. So what is actually happening here? Before we saw there was a compile error, and then the compiler will try to look in the implicit scope, is there something with which I can make this work? And if we define this balance to int in the implicit scope, it will actually find this and it will work. So what is actually being executed here is balance, is makeString balance to int, on this balance we defined. This is what is in the bytecode in the end. Okay, so there are also some converters and conversions built into the Scala collections library. So given that we have a Java list, for example, when you're working with some Java library, this can happen, of course, when working in Scala. And we have some method in Scala which is expecting a Scala type sequence in this case, which will just print it for now. So we define this, and we want to use it with the Java list. Well, this will not work because again, it's the wrong type. So you already see this coming, of course. We define an implicit conversion, but in this case, it's already present in the Java collections library. So here we import Java conversions _, to bring all the conversions for Java collections in scope. I see already someone making pictures. This is not the way to do it. You shouldn't use this. So of course this will work because under the hood it will use the implicit conversion to make it work. So the better way actually is to use Java converters, which is a little bit more explicit while still using implicits. So what's happening here is that we import this, and now this Java list can be upgraded to another type, which will actually have this Scala method defined on it. So now it's less magical than it was in the first case when we were using the conversions. And the reason why this is a better approach is that in this example we're converting some collection from Java to Scala. It might have different semantics. It might, for example, evaluate a whole stream, make a list out of it, and do something under the hood that you are not expecting. So it can lead to very weird behavior, and you cannot see it in the code directly. And this thing is still very powerful, but you have to write a little bit more, but therefore it's also more explicit. Okay, so this leads to another subject, because what we actually just saw was an implicit view already. Let's start at the beginning here. So if we define a simple wrapper class, string wrapper, which will take a single argument and will give us an extra method here, which will just put quotes around the string. So we can call it like we would expect. We call the constructor with myString, and now we can call this quoted thing. But wouldn't it be nice if we can just call it like this? So call .quoted on the string directly. Well, this will not work because we don't have this method on string, and we don't have control over string to add this method ourselves. So what we can do is we can define an implicit conversion again from this string to string wrapper. We call this a view. So implicit def wrap string, which takes a string, will give us a string wrapper, and it will just use the constructor here. Now, if we try to run this code, instead of not compiling, it will try and make it work by using an implicit. So it will look into the implicit scope, will see the wrap string method, and will apply it before. Oh, I should got to run it, and it will apply it to the myString, and now it will work. So what we see here is we actually made a view on string named wrap string, and then we can add. Well, it seems as if we are adding methods to string in this case, which will actually also it allows for very powerful DSLs, for example, to be written. View bounds, yes. So we see this operator here, lesser than percentage. So T, less than percentage, string wrapper. This is actually deprecated by now, but you might see it in code, so that's why I put it on here. So what this means is that you can call this method, but only if there is an implicit view available from type T to type string wrapper. So if we try to run it with a string, it will work because we previously defined this implicit def. As you can see here in the REPL, there's some other syntax going on here. So we have some def using quoted strings with a type parameter t and one parameter here. But now we have this extra parameter list with some evidence $1 here, which will provide the view for us from type t to string wrapper. So yeah, as we just saw, this is actually syntactic sugar, the smaller than percentage sign, for an extra implicit parameter list. And actually, yeah, this is the new way of writing it, by being more just being explicit about that implicits are being used here. And it will work. Okay. Of course, if you try to call your created wrappers on values that do not have an implicit view available, the compiler will complain no implicit view available from int to string wrapper here. So what we saw is that we were constantly defining implicit defs. You can also put an implicit function in scope here. So, well, I see I've now written down def here. This could also be a val, of course. So if we make some string wrapper, which is actually a function, this will also work for the implicit view way of working. So we see that this also works. Good. Because now we have an implicit view in scope for int to string wrapper. Another example from the standard library. You might all know this. So what we see here is actually the same as writing 1 to 10 with the dots in between and the brackets around it. And what you get is this range here. So what we see is that this 2 is a method defined on 1 apparently. Well, as we all know, 2 is not defined on integers, but it's defined on a view on integers, which is called rich integers. So in pre-def, there's an implicit conversion defined for you from int to rich int, which allows you to write these kinds of things. Another example that works is the tuple syntax. If you have one arrow a, this method, arrow, is not defined on 1, but it is on, I think, wrapped any or something like that. So it allows you to have this extra other syntax to create tuples in this case. Okay, implicit classes. So this is another manifestation of implicits. So given that we have some balance case class, but it's defined in another library, so we have no control over it. Yeah, we have no control over it. Next. Oh yeah, what I want to show here is we see this minus balance here, but we don't have this method available. This syntax is a way to write a prefix notation. So if a method with unary underscore is defined, you can actually put it in front of your value. So this should only work if this method is available on balance. Well, it isn't, so we cannot use it. Here, an implicit class can be very useful. So note that we write a class here with implicit in front of it. It has a single parameter here of type balance, and we define this unary underscore minus on this, which will just invert the balance for us. So given this implicit class, we can now actually call minus balance, and it will work. So this is a bit of a combination of what we saw before, because first we had the implicit conversion from the string to string wrapper, and that allowed us to call methods on the string wrapper as if they were defined on string itself. But then we had two parts of it. We namely had the string wrapper we had to write, and we had to write the implicit conversion. And as you might have noticed, there were some compiler warnings as well in between. Please enable implicit conversions is an advanced feature. Please enable this explicitly with a flag, because things might go wrong. If you use implicit classes, you do not have this warning, and you can still use it as this, where you actually wrap an existing type where you don't have control over, and you can add methods to it, which is really powerful, I think. Yeah, implicit classes can extend other libraries and types. Yeah, so let's go back to the slides for a bit. Yes. So this is very interesting, of course, and I hope you have seen some of the ways of using it. But what is exactly this implicit scope, and how does the compiler resolve all these implicit values? So I actually found a comment of Martin Odersky on one of the blog posts about implicit, where he explains it in 2 simple steps. Basically, when the compiler is looking for implicit, it will look first in the local scope if it can find something which is referenced by only a simple name. So that means no dots, basically. So if it's available with a simple name in the current scope, then it will use it. Obviously, it has to be defined with implicit in front of it. If it cannot find it, then it will look further, namely in the companion object or the package object of the type involved here. So in the case of implicit parameter in a method, it will actually look at the type you pass in the companion object, but it will also look in the type that it is expecting in the companion object to see if there's some conversion available to make this work. And then, if it cannot find it, then it will also look in supertypes and supertraces of this. So we'll see an example in a bit of this as well. So the reason for this distinction is actually that it is quite a sane default for developing libraries. So for example, I'm a library developer. I define some implicits which I put in a companion object of my types that I'm defining in my library. And then if a user uses my library, it will find those implicits because they're in the correct scope, namely in this second part, the companion object. Now, if my user of the library wants to have different behavior, wants to use different implicits than the ones I specified for him, he can define implicits in his own scope, which are referenceable by a simple name. Or he can import them from another place explicitly, so they become available with a simple name. And this allows for the library definer to set sane defaults, and for the user to override them if he really wants to. So let's take a look at some scoping. There it is. So let's go through this slide first. So for this example, I created a case class here, which is simple as a content of type string. We can create a companion object case class, which contains an implicit file of type case class. We define another object named explicit, which also defines an implicit file of type case class, and a wildcard which also contains one. And now we define this method here, find case class, which will require a case class that it should get somewhere from the implicit scope, and will just return it for us. So now I'm curious if you guys have an idea what will happen here. So if you think that this will actually result in the case class in the companion object being returned, please raise your left hand. If you think if it in the explicit, raise your right hand, and for the wildcard, just raise both hands. So, what do you guys think? So left hand, my right hand is for the companion object, and the other one's for explicit. So, yeah, I see a lot of left hands. Let's see what is actually the case here. Yeah, you're correct. So, because there is nothing with a simple name in the implicit scope, it will not use it, so it will fall back to the second rule, where it will look in companion objects of the one of the defined of the target type in this case. So it will find the implicit in the companion object. So now another example. What if we actually define a local case class here? So same holds. If you think it's in companion object right hand, explicit left hand, wildcard both hands, and if you think the local case class is being used, then put them together. Well, let's see what's happening here. Defined in local val, yes, because it's available with a simple name, it will pick it. Next one, import wildcard dot underscore. So this is a wildcard import. So a companion object explicit wildcard, no wildcard. No, we don't need that anymore. So what do you think? I see both hands there. I see some together, which we don't use anymore. So let's take a look, defined in wildcard. We use a wildcard import, so it becomes available with a simple name, and it will resolve like this. Now we do an explicit import by referencing the explicit. Well, you obviously get the drill. This is the last case. We will use the explicit object now. So what do you think will happen when I do both of them? So I do an explicit import and I also do a wildcard import. What will happen here? So we again have the companion object, explicit, and a wildcard. What do you think? See some wildcards? Okay, let's take a look. Well, this was a bit of a trick question because I left the option out that it doesn't work. So now it's available with a simple name for both of them, because the wildcard import makes it available under the simple name as well, same as the explicit import. So the compiler cannot decide anymore on what to pick here. So it will give you compiler error and you have to fix this yourself. Next, we have another case. So what I did now is I defined some trait parent here, which contains implicit val, and I use it in the companion object. So this is to show that it is also looking for the supertypes of the involved types. So in this case, defined in the parent of companion object. So when this is useful is if you have, well, in this simple example where we just have simple case class, this doesn't really work. But if you have like a more involved type with some mix-ins in there, you can go from most specific to least specific also in the inheritance of your companion object or your package objects. Okay, well, this is for the next part. So let's go back to the demo here, to the slides here. Yeah, so I hope I gave you a bit of an idea of how resolving works and where to look when things go wrong. So let's look into type classes for a bit. So type classes are actually coming from a programming language called Haskell. And they need them there because they do not have subtyping, because you can use it to do overloading of methods and operators. Well, Scala has subtyping with inheritance and everything, so you can achieve the same things without type classes, but they prove to be very useful as well. You actually use them when you want to extend libraries which you do not have control over. So some of the patterns we saw before come in use here, and that's also because if you want to implement them in Scala, you are using implicits for this. In this case, we have this example here of numeric, which is defined in the standard library. So if some type T has a numeric of T as well, we know that this set of operators is also available on this type T. Okay. So let's take a look at an example again. So first, so this is about the JSON serialization. We have some model objects that we want to serialize to JSON, and we can do this in a naive way using subtyping. and then we'll look into the way doing this with using a type class. Okay. So let's take a look. We have this trait JSON serializable, which has a toJSON string, and for now we'll just use string for the JSON type to make it simple, keep it simple. We define this. Next we define some model classes. So we have a case class account here, a case class payment, and a case class person, and they all extend from JSON serializable, and therefore we have to implement this toJSON string. So I just write everything out for now. Just fill everything in. So this is quite a lot of code, but it works. We can create an account, we can create a JSON string, and it will work. But obviously we have really cluttered our model implementation here by putting all this JSON serializable stuff in it. And of course, you can make errors very easily. First name, and this is also first name, so it doesn't make sense. So lots of manual work, but we can do better with type classes here. So the type class approach. If we have our model object with the same case class defined in it, but now we leave out the JSON serializable, and we create some value objects, some values here to use in the examples. So this will work. Now we define a type class here, trait JSON writer T. So it's a JSON writer of type that can write types T. So it contains one method that wants to have something of type T, and then can convert it to our JSON type string here. So what we can do now is we can create some implicit JSON writers for the types that are applicable for us. So we see here the JSON string, which will create a JSON string for us. It implements the JSON string method, and what it will do is it will just put quotes around it. For big decimal, I do something similar. I create a new JSON writer big decimal, I implement the method, and now what I do is from the implicit scope, I summon the JSON writer for strings. I convert the big decimal to a string and then use the JSON writer to actually create the JSON value of it. So what you see here, instead of doing this, I could have also just referenced JSON string directly. But it might be that this JSON string is defined somewhere else, in a library, for example, or that I do not know the specific type of string here. In this case I do, so I could have used it. But we'll see an example next where we cannot do it like that. So now we can define a JSON writer for our account, for example here. We implement the method again. We summon the implicit JSON writer for string and for big decimal, and we use them here to serialize the values of the case classes. Now, if we grab the JSON writer, we can use it to serialize my account. I think I forgot to run this one. Yes. So we use this JSON writer now to write this to string, but the syntax is still a bit boilerplatey. What I would like to write, what I could do with the naive approach we saw before, is just do myaccount.toJSON. Well, given the examples we saw before, we know a way how we can accomplish this. So we can create an implicit class which will take something of type T, and it will need something to serialize this type T, namely a JSON writer T, and we define it as implicit, so it will grab it from the implicit scope for us. And now the implementation of this JSON serializable is very easy. We have this def toJSON, which will use the serializer from the implicit scope to serialize our type T to our JSON type. We can run this, and now we can also serialize our account like this. So what we see here is we actually used implicit implicit values here for JSON writer T, and we also use implicit class to add some methods or well make to JSON available on our model class in this case. We can generalize this, of course. So let's first look at the top part. We can create a companion object for JSON writer, because as we saw, the JSON writer is just something that converts a type T to our JSON type of a string in this case, which we can make easier by just passing in a string. So we make an apply method on JSON writer, so we can write something like this. I don't know, I type int to I2 string. So this is a perfect valid JSON writer now if I would have evaluated the slide first. So that is. I don't know why this doesn't work, but it's not really relevant to the story. So given that we can use this apply method, we can now define a JSON writer for map. And for JSON this makes sense because you have lots of key value pairs, so if you have a map and you can serialize that to JSON, it will make things a lot easier. So we see some extra syntax here. So here we see k colon JSON writer and v colon JSON writer. This is what we will use to serialize the key and the value pairs here. And in the end we want to create a JSON writer which can serialize the map. So I've written down here that these type bounds that we saw here with the colon are nothing more than implicits that should be available. This is exactly equivalent to this notation. So given some k and v, we also require that there is a JSON writer k implicitly in scope and a JSON writer for v implicitly in scope. Otherwise we cannot call this method. In the implementation, I just loop over the values in the map because of the implicit class we defined earlier, and because these k and v are also available, there are also JSON writers available for them. We can actually call these to JSON on them for the key and the value, and we just join them and put some parentheses around them. Now if we run this, we can actually serialize maps now. So we have A1, B2 in this case, and it will work because we only use strings in here, and we have JSON writers available for the strings. So we also have a JSON writer available for map string. And it will all look this up for you in implicit scope. So now what we see is that because we have JSON writer for string, we also have a JSON writer for big decimal. We can use these types to actually lift other types to JSON writers as well, given that their parameterized types also have valid JSON writers. Now we can use this for our model again. So what I do here is I make a JSON writer for model payment in this case, which contains 3 fields: the from account, to account, and the amount of money that has to be transferred. And what we can do here is we can just create a map of the items, and because we have a JSON writer for maps available, we can do toJSON on this to create a JSON writer for models here. And now if we do payment, which is our value object we defined earlier, we can actually output this to a nice string form, JSON format. Of course you can even go further with this, but that's maybe a bit too far for this talk. If you have a case class, you can see this as an age list of its fields, and you can write some generic code that for all age lists you can create JSON, given that for all of the types in the age list JSON writers are available. And this is actually how many of the advanced libraries work. So this was the end of the demos. Let's go back to here. Yeah, this was actually most of what I wanted to talk about. So I hope I've shown to you that implicits can be quite powerful. You need to be careful with implicit conversions. For example, if the semantics of the conversions don't match, it can lead to very complex conversions happening that you might not see when you just look at the code. They really help with building expressive DSLs and extending libraries, for examples. You can even do dependency injection with them. And maybe the thing I want you to take away from this about the scoping and the resolving of implicits is it will first look in the local scope. If it doesn't find anything, it will look in the campaign and package objects that are relevant for any of the types involved in the conversion in this case. And type classes are a very powerful means of extending libraries without having to clutter the libraries with all kinds of things in a non-intrusive way, basically. So that's what I wanted to talk to you guys about today. Are there any questions? I see a question here. I think there's a microphone coming from somewhere. Tips on debugging. So that's an easy question, a short question at least. What you can do is you can always look at the bytecode, of course, what is actually being used there. More easily is maybe to let your IDE help you with showing what conversion is, for example, being used, or where this object is actually being defined on. That makes sense. I see another question there, at least.
If you have an implicit conversion that goes from A to B, and another implicit conversion that goes to B to C, does it automatically convert A to C?
That's a good question. Well, the compiler actually only does one implicit conversion to not blow up the search space for implicit, and also to make it a bit more sensible about what is still happening there. Yeah, good question. Yeah, I think there was a question here in the front. So what I know about this is that the package that it also looks at implicits in the package object was added more recently, and I think well, to be honest, I'm not quite sure about this. I would personally put things in campaign objects and put them closer to the types, but the Scala compiler actually allows package objects to also be used. Yeah. Question in the back there.
Hey, when you were doing the implicit precedence part of your talk,
Yes.
The first time you had two implicit conversions in local scope, there was not a compilation error, and the second time there was. Can you explain why it compiled the first time, when you had one defined in local scope and one imported from the companion object?
So I first had two implicit ints in scope, I guess, or I didn't fully understand the question.
You had two implicit conversions in the same scope, local scope, and there was no compiler error. And then the second time, there was a compiler error. So maybe go back to that slide.
Yeah, maybe that's the easiest way. So it's in one of the examples, right? So I can go back there. So you mean this example?
Yeah.
So this one becomes available under a simple name because now we can reference this under this name.
Not that slide.
Next slide.
Previous. The one where you had the local scope conversion and the one from whatever object, companion object.
So this is the example where I actually show that also the subtypes are being used here.
Okay,
maybe
two previous to that.
two previous.
Before that.
So here I import only the explicit one. So, and this one is the wildcard import.
I'll just ask offline.
Yeah. Maybe we can talk about this after. Any other questions? I'm not sure how I'm doing on with the time. But, Well, if that's it, well, thank you for your time, and I hope you learned something.